Okay, we are going to talk a little bit about power amplifiers. We did talk about output stages a while back, and we talked about class A, class AB, class B, and we kind of like touched upon class C amplifiers. But we're thinking about it as an output stage more than anything else. Now, what we are going to be doing today is more focusing on power amplifiers that are intended mostly for RF applications. So they're generating high frequency signals at certain frequency or certain frequency ranges. And they are producing this power with reasonable efficiency. So efficiency is one of the parameters that's important when you are making power amplifiers and output stages and things of that sort. And the reason, as we discussed before, is that it basically sets the amount of total energy that you spend to a good degree, because that's the most power hungry stage in your amplifier chain usually, because the one that has the most power. So the key question is that how do we do this? So the focus today will be a little bit about, mostly on RF power amplifiers, and it's an introduction to that, and with a fair amount of focus on switching power amplifiers, although we are going to be talking about non-switching linear ones along the way. So before we start talking about specific topologies and things of that sort, there are certain rules and relationships that matter in power amplifiers. And there are certain ways, kind of like a spectrum. If you think about a power amplifier, they really form a spectrum. If you think about purely linear one, class A, where you bias the stage, the operation point, at the point where you have the largest range of linear operation, meaning that you're trying to be avoiding turning the transistor off, or putting it into triode or saturation if it's a BJT or something like that. And that would be class A, which is on the left of the spectrum that we're looking at. And then, as we saw before, you can go to class B, where you basically turn the transistor on for half of the cycle. So your current is basically on for half of the cycle while the voltage is going through. So you basically presumably have two transistors that provide this one, or a resonance circuit that captures the energy during the time where the transistor is on, and through its resonance behavior produces the voltage that's mostly sinusoidal. So you can do this either as a resonance circuit, or you can do it as a double-driven stage where half of the current is driven on each side for half of the cycle. So you can see in these plots that usually, by the way, in all these plots that we're going to see here, the voltage is red and current is blue, just so that sometimes you don't have them labeled explicitly. And then the other end of the spectrum is basically when you make it more and more switching. Now, let's ask this question from ourselves. The energy that's lost on the transistor itself, the power on the transistor, is primarily determined by the product of the current in the transistor. Let's say if it's a MOSFET, the drain source current, the drain current, and the drain source voltage, right? Because by definition, power is the product of the voltage and the current. So, and that's a power that turns into what? It turns into heat, right? Because that basically heats the transistor up. That's the power that's dissipated in the transistor. If you're trying to maximize the efficiency, one of the things that you want to do, at least if you're trying to minimize the loss in the transistor itself, what do we need to do? Ideally, we want to make this product zero, right? Well, one way to make this product zero is having one of these parameters being identically zero, which is useless, because then you will have no power output. But the other thing is to create two waveforms whose product is zero while they are independently non-zero. So the idea here is that if you want to have the minimum amount of loss in the active device, in the transistor, you want to have waveforms that look more like the waveforms on the right. Meaning that your voltage is non-zero when the current is zero, and the current is non-zero when the voltage is zero, right? And in this way, the product of those two will be zero, at least theoretically. If you can make these ideal waveforms, then it would be zero. And that means that the power dissipated in the transistor will be minimized, or zero if they were theoretically zero. And that would imply that you can actually, then you are limited by other losses in the circuit. For example, if you have a resonance circuit or things of that sort, the energy loss in those matter. Now, what happens in this spectrum, I mean, these are some points along this spectrum of things, is that there's a trade-off between efficiency and linearity. At least the linearity, straight up linearity, meaning that if you put a sinusoidal waveform input, how sinusoidal, how much the output deviates from a sinusoid. So an ideal linear circuit would produce another sinusoid that's amplified in power. An example of a nonlinear circuit would be one where you basically have like a square wave coming out, or some other waveform, right? That's what we mean by linearity in this context. So as you can see, when you move to the left, you have more linearity and gain, and when you move to the right, you have more efficiency for the reasons that we discussed. There are a couple of scaling for laws for power amplifiers that are interesting to discuss, but to do that, let's have a simple model for a switching power amplifier. Now, if you think about a switching power amplifier, and if you want to abstract it, we want to create something that has non-overlapping voltages and currents, right? As we discussed earlier, to produce the minimum amount of loss. Now, if you use a switch, as shown on the lower left here, what you will see is that if you had an ideal switch and some mechanism, let's say a very large inductor to maintain a constant DC current, they call it RF choke sometimes, to produce this current, then by turning the switch on and off, you can presumably produce some sort of a waveform here, and through a passive network, what we call the output network, you can convert it to the waveform, the desired output voltage. Now, the voltages we are showing here, the red voltage here, is the voltage across the transistor, across the switch, not the output voltage. You want the output voltage to be close to a sinusoid. So we are talking the voltages and currents shown in this plot on the upper left are the voltages and currents across the switch itself, as shown in the picture. Now, the problem of a switching power amplifier design, really to the first order, is designing that passive network in such a way that it produces the desirable waveforms, voltages and currents, on the left side while it delivers load to the output. So it's a network synthesis problem in that sense, in general, from that perspective, right? It's a passive network synthesis problem. Now, the question is that there are many, many different approaches to that. Now, if you think about the simplified model, there are several scaling rules. There are a couple of scaling rules. We call them waveform scaling rules. Now, one is if you had something, let's say you already had a VDC, the DC voltage across the output. Now, if you scale the DC voltage by factor lambda, right? Here. If you scale it by factor of lambda, the question is that what would happen to the waveforms, currents, and voltages? Now, if you're using a switching amplifier, although it's a highly nonlinear device because you're switching, turning on and off, this scaling rule holds exactly, which means that both your current and voltage will proportionately scale if you increase your lambda. So you will get the same, if your network remains the same and your switch properties don't change, the waveforms will remain exactly the same. They would just, both current and voltage would scale up proportionately. It's a useful thing to remember when you're designing amplifiers. Another thing that's interesting is the picture on the right, which is the impedance scaling. The impedance scaling tells you that if you actually now took the impedance that you had and scaled the impedance by factor of lambda, right? As you make the impedance larger, your current will go down, but the voltage remains the same. So scaling of the impedance, if you take that impedance network and scale it, would only change the current and will increasing that will result in reduced current, but will not change the voltages across this network. I mean, these may seem obvious and simple, but they apply properly, they can provide additional insight. Okay, so now if you think about it, there's another spectrum, there's another kind of range of variations in a transistor, in a power amplifier. You can have the same, through the scaling laws that we talked about, you could think about having designed a certain kind of amplifier with a certain current and voltage waveforms, with certain current and voltage waveforms, as shown here. Let's say in this case they're non-overlapping, so they're good designs, they're pretty efficient. And through scaling, we can actually have ones that you scale the current down and voltage up. So just basically make the voltages larger or current smaller, while maintaining the general shape. Of course, if you move to the left, you have more current and less voltage, and to the right, you have more voltage and less current, right? Again, this is somewhat of an obvious statement, but why does this matter? It matters because the choice of the devices you're designing with determines where in the spectrum you will land. So for example, let's say you're using some RF gallium nitride transistors for your design that have high breakdown voltages. Let's say your transistor has a breakdown voltage of 50 volts. Right? Then your design should be more towards the right, because you have the ability to have a large voltage swing, and you want to minimize your currents because you want to minimize the other I squared R losses in the circuit and all those things, right? So for that, you will be moving more to the right of the spectrum. Now, let's say you're using kind of very small scale CMOS transistors, right? Let's say you're using CMOS transistor with a breakdown voltage of like 1 volt. Then if you are trying to deliver the same amount of power, then you will have to operate more on the left, which means that you need to be operating in create situations, and we'll discuss this in a lot more detail in practical settings, where you need to produce large currents and small voltages. And that scaling matters, the way you think about that. Okay. Now, now that we started talking about the transistor technology, now there are several figures of merit or demerits, depending on which one we're talking about, for different kinds of amplifiers. Now, if you're making a linear power amplifier, as shown on, for example, on the upper left, pick that cyan box, what you see here is that you have a transistor and a tuned load, right? You have a parallel LC network and some RF choke to provide some DC current, right? Now, the question is that how do you bias this? If you're using it as a linear amplifier, you want to make sure that your device remains let's say if it's a MOSFET, it remains in the pinch-off region, or if it's a bipolar transistor, it remains in the forward active region. So there are two voltages that determine the boundaries of this limit region, right? On the lower end, this voltage where you transition from, let's say, triode to pinch-off, right? We call this the knee voltage, VK, because it looks like a knee, right? Bent knee. And then on the right-hand side, you have the breakdown voltage, VBK. Okay? And then these two basically determine the range that you can operate. And you can see that even if you use the perfect load line, a linear load line, which corresponds to a linear amplifier, class A amplifier, for example, then the maximum efficiency you can get is proportional to the 1 minus VK over VBK divided by 1 plus VK over VBK. And we saw this in the lecture earlier on. We did this derivation or something along these lines. So however, this number, this VK over VBK, or this equivalent eta that we showed here, is the parameter that would be used to evaluate a given transistor technology, right? Say, okay, what is the best efficiency I can possibly get from this if everything else were perfect? Now, for switching power amplifiers, we'll introduce two figures of merit, really, that are important. One, and they have two figures of merit because they're two different scenarios. Now, in a switching power amplifier, the actual switch looks more like the picture on the upper right, right? What you have here is that you have an ideal switch. It has an on resistance, and you have a capacitance associated with it, which will be present when the transistor is off, right? And when it's on. So if you look at this, if you scale the transistor up, basically meaning you take the transistor and take another copy of it and put it node for node parallel, right? What would you do to these parameters? R on would be half, right? And C out would be doubled. But there's one thing that doesn't change, which is the product of these two, the RC product. So RC product is independent of the size of the transistor, and therefore can serve as a figure of really demerit, because you want it to be as small as possible, right? Now, for a situation like this, so this is a scenario where your capacitance is limited, meaning that the transistor size is limited by the maximum C out you can tolerate. Now, why would you have a tolerance? Why would you have a limit on C out? Well, it's a choice of that passive network that follows the transistor switch, right? So we said that we are going to make this network of Z, impedance network Z afterwards that we can synthesize, and that would determine how the transistor works. And how the amplifier waveforms will look like. So that can tolerate a certain amount of capacitance, because that capacitance becomes part of that network, right? If you make it with a certain design, and then you put a gigantic capacitor in its input, the network has changed, and therefore it will not perform as you expect. So that's what we mean by capacitance limit. Now, in this scenario, the losses are really determined by R on C out. And the loss would be proportional to this product, that this R on C out product, times F, because that's the number of times you switch and you charge and discharge your network, and the total power, of course. The more power you have, the more loss you have, because it's proportionate, right? I mean, if you're losing 10% of it, 10% of 1 watt is smaller than 10% of 10 watts, right? Okay, so that's the figure of merit for the device. So if you have a transistor, if you want to evaluate it in this scenario, the first number we look at is R on C out. Now, there's a second scenario, which is basically when you have gain limited system. In this case, basically meaning that the size of the transistor is limited by how much power you are providing to the input. And this is an important parameter if you're looking at the power added efficiency, as opposed to just pure drain efficiency. Now, the difference between these two is that the drain efficiency is the ratio of the output power to the DC power that the amplifier draws, right? But I can make a device, I can suggest a device to you that has 100% drain efficiency, which is a wire. Because the drain efficiency doesn't take into account the input power. It in fact can have even more than 100% because you're providing more power at the output than you're drawing from the VDD, right? So the drain efficiency, in that sense, is not a very good metric. I mean, this is an absurd example, obviously. But now, so there's another metric, which is the power added efficiency, which basically takes the input power into account, right? And it's basically, it takes both the output power and input power into account. In this scenario, you can't care about how much power you drive into your amplifier, meaning that you need to have gain in your amplifier. Right? So if you have an amplifier that has very little gain, it means that, yes, maybe you can generate a lot of power at the output, but you need to drive it with almost as much power at the input, which defeats the purpose. So in those scenarios where you're gain limited, then the figure of merit changes. So the losses would be proportional to this parameter, where basically you have the R on and R gate both matter, and the quality factor of the gate, that's determined the gate input network, which is consisting of the gate series resistance and the capacitance of the gate. Now, this is a different scenario, and in this case, your figure of merit slightly changes, so you usually evaluate both of these things. So now that we've understood these things, the next step is how do the waveforms look like as we go through the spectrum of the amplification and different classes? I'm not a huge fan of naming these different classes with different letters and things of that sort, but that's a convention, so we stick with it. But in general, they're just basically, it's a continuum of things. And it's probably more, like any other continuum, it's more defined, as opposed to defining it's convenient to define colors by their names, but then different people have different resolutions. There's another way to define colors is by wavelength, right? Which is very quantitative and repeatable and accurate. But anyway, so we are defining their colors by names here. So if you think about, so let's start with this, the more linear amplifier. So let's say you have a class A. So what you have for a class A amplifier is a load line that looks more on the one, like on the one on the left. So you can see that if you have the IV characteristic curves that look like this, a class A amplifier moves from between the breakdown voltage and the knee voltage and tries to stay in this region. And if you look at the waveforms associated with that, then you will have a continuous waveform on the voltage and current in that case. So as you transition to, for example, class AB, as the load line becomes more and more bent, you transition into class AB and the load line becomes more steep. And then for class B, you have a load line that looks like the one in blue, which corresponds to the waveforms that are shown on the right-hand side. And you can see that your current is on for half of the cycle. The voltage is basically more or less sinusoidal. And then if you go beyond that, if you make your duty cycle less than 180 degrees, or less than 50%, then you basically are venturing into the realm of class C, the so-called class C, which again corresponds to even a steeper load line with a larger knee. So basically you're transitioning between the right and that green dot on the right hand side of that x-axis on the left, and the other green dot on the top where the knee happens. Right? So you have this transition that's kind of less linear, and you're transitioning between those 2 points. That's basically as you're operating, your operation point moving. Now, this is when you don't overdrive your amplifier. If you overdrive your amplifier, meaning that your input is larger than expected, your currents will start behaving in this funny way, as you can see on the right-hand side. So what you see is that your currents, instead of being this kind of like a single bell-shaped lobe, they go up, and then there's a little dip in the middle, and they come back down. And the reason for that dip in the middle can be better understood by looking at the plot on the left and that orange overdrive part of the curve, which basically means that you're now going into the transistor is going to a triode region, or saturation for a bipolar transistor. And what happens is that you just overdrive it. The voltage across it significantly drops, so it doesn't start drawing that much current. And the load line, instead of going up, it goes back down, which corresponds to a smaller current, as seen by that orange dip in the middle. And that's something that you see a lot in amplifiers if you overdrive them in the waveforms of the current. And if you see that, that's a telltale sign of an overdriven amplifier. So now, if you look at these stages, so these classes, again, the waveforms are shown here on the right-hand side. So if you look at it, for example, in the 4 plots on the right-hand side, you have class A, where the input current and voltages are both kind of more or less sinusoidal looking. Now, as you go to class AB, the current starts becoming more and more saturated on the bottom, hitting 0 more frequently. Class B is where basically you're off for half, the current is off for half of the cycle. And class C is when that duty cycle is even going below 50%. Right? So these are the typical waveforms that you will see in these classes. And as you can imagine, this is a continuum. We're just like naming, and the naming convention is kind of a funny thing because class A is a point on that line. Class AB is a big line, big part of the line. Class B is, again, a point. And then you have C, which is like another part of the continuum. But again, it is what it is. OK, so now how about other switching amplifiers? The concept of switching amplifiers, so this is like an example of class D or class F. So here the idea here is that you're doing more waveform engineering. Right? You're trying to design the desired waveform. So at least conceptually, what you see on the left-hand side is what, for example, could be a class F amplifier. Now, the class F amplifier, the idea of a class F amplifier is that if you look at it in this example, and this again conceptually, the way it's shown, there's a bunch of parallel branches, series branches in shunt, and a bunch of parallel LC branches in series. Right? So what do? The series LC branches in shunt, like the one that says 2F0 and 4F0, in this case are going to be short-circuited, at least, or have a very low impedance at those frequencies. Right? So in this case, at second and fourth harmonic, you're short-circuiting this. So, and the series, the parallel ones, that's 3F0 and 5F0, are going to be open circuited at those particular frequencies, right? So what you're doing, you're short circuiting in parallel at those even harmonics. So what does this do, if you think about this? They would affect the voltage and current, right, at even and odd harmonic. Now, imagine for a second, forget about this, and imagine that if you wanted to create a voltage waveform that was a square wave, what would you do? A square wave with a 50% duty cycle would have only odd harmonics, right? And it would, if you have the odd harmonics in the right proportion, you can actually create, and in the right phase, you can actually create a waveform that's like square wave. Now, why do you, for example, would you care about a square wave voltage? Because if you could generate this, I mean, this is an idealized waveform, obviously. In practice, they would never look like that, as clean as that. But if you could do that, it allows you to get to the maximum voltage, operate very close to the knee voltage, or breakdown voltage, sorry, not the knee voltage, the breakdown voltage, and stay there. So if you have something that peaks close to the breakdown voltage, you're limited by that peak. But your voltage will not be optimum because at other points it will be less than the peak. But this way you can keep it as close to the peak for as long as you want, for as long as possible, right? And this is a useful property, for example. So you can do waveform engineering, and then the associated current waveforms would be the ones that are shown here. Now, this is our class F. This is a class F. And the challenge, one of the major challenges with the class F is that this capacitance, this CS, this capacitance of the switch, CS for switch, is going to actually cause you a lot of trouble. How so? Because if you think about it, these networks only operate as that idealized short and open network when that capacitance is 0, when it's driven with an ideal switch. This capacitance becomes part of this network, and then therefore it limits how large you can make your transistor, which basically then limits how much power you can generate. So this is one of the major challenges in a class F amplifier. What to do with that capacitor? Because in theory it looks very nice. As soon as you attach a real transistor to it, it doesn't work as nicely anymore. Now, each one of these classes has an inverse. What do we mean by inverse? Which is shown as d to the power of -1 and f to the power of -1. By inverse, we mean that the voltages and current waveforms are switched. So what looked like a voltage waveform becomes a current waveform, and what looked like a current waveform becomes a voltage waveform. So now the question is that how can you make something whose current waveform looks flat like that, and the voltage has that other shape? And this is actually in a way easier because, for example, if you have a differential one with a balanced, properly tuned load, you can actually create this kind of current. Now, this is useful because of certain things that we'll see next, which is another class of amplifier, class E, which is an interesting class. So this is a perfect example of intelligent synthesis of the network, right? So, and this was done by actually a father and son. It's a famous paper by SoCal and SoCal that introduced this Class E stage. And it's very interesting because they designed it, they went through analytically designed an LC network that would produce not only this non-overlapping waveforms, but it also has what we call the zero voltage switching, which basically means that you switch at the time that the voltage is zero, which would, and they try to also control the slope of the voltage. So not only they control the value, but they control the slope, which would have an impact in terms of the capacitive discharging losses and things of that sort. So it's even more optimized. And this waveform is nice. Now, the most useful thing about Class E is that this capacitor is part of that network design. So that design actually includes that capacitor. So whatever you design for, you can allow for a certain amount of capacitor, and that capacitance becomes part of that network, and you just account, and in your network that they actually explicitly place there, you place the difference, whatever extra capacitance you need to get to that total capacitance that you need. And this is a very useful property. So now the interesting question is that, is there a way to combine, for example, this good property of Class E and some of those interesting waveform engineering, waveform engineering aspects of a Class F? And an example of that is what we call the Class E over F odd. Sometimes people call it Class EF. It really should be pronounced E over F because it's an F inverse combined with an E, not a regular F. So and that's why there's a slash. It's really a division. It's E over F, or it should be E F to the minus 1. And odd meaning that we only do the harmonic control on the odd harmonics in the Class F. And this basically, this topology on the left allows you to do that. Basically, it allows you to absorb these CSs, these capacitors, these switch capacitors, and it also allows you to create waveforms that are non-zero, zero voltage switching. So in principle, it allows you to also operate at higher currents with a given voltage. Now, all of these can be actually summarized in this table here. So this is like the summary of all these results, what each one of these classes allow, and things of that sort, and examples of what the efficiencies would be, what do you do with the capacitances and all those things, and the output versus load product, the output power versus times load product, and then the output power and breakdown voltage products. So that's actually an interesting thing, and then you can look at them a little bit more deeply if you really wanted to. And then you can also do some wave overtone control, right? I mean, this is the other interesting thing that's controllable. The path that you take, actually the trajectory that you take for the current and the operation point, you can actually control it either to be on a straight line or have some sort of a hysteresis in practice because of the capacitor. And this allows you to do some sort of a waveform control. So now, having said all of these things as a background, now let's look into some practical questions about design of power amplifiers, in particular in CMOS. Now, why we would want to be making RF power amplifier in CMOS? Because if you look at the typical radio, now these radios happen everywhere, right? I mean, you have a cellular phone, you have a Wi-Fi receiver, you have Bluetooth, you have all sorts of other systems that use radio transmission. And a radio transmitter and receiver, or in short, a radio transceiver, consists of, typically looks like that. The concept is that you have an RF transmitter and RF receiver. You usually have a separate power amplifier that in many cases, if the power levels are high, is not implemented in silicon CMOS. And then you have the baseband processing and some microprocessing. And now, a lot of this is basically what we call a single chip radio. If you could make a decent CMOS power amplifier, one of the long-term things you could do, you could actually integrate all of that into one chip CMOS chip radio, a single chip CMOS radio. And then eventually, even for high power systems, you could have a single chip cell phone or single chip radio and things of that sort. And these are kind of happening right now, and there will be more and more of that. Of course, for low power systems, it's already happened, right? If you have a Bluetooth, the entire system is on a chip. Now, if you have a cellular phone or things of that sort, then it may not be still. I mean, some of them are happening and have happened in various forms. So why do we want a CMOS power amplifier? There are various reasons. CMOS technology is very low cost in volume because you can actually make it. We talked about the economics of this a while back. And the economics of it is basically such that it allows you to make it in large volume with large wafers. You get very low cost. So cost is important, especially things that have you sell a large number of them. There's a lot of capacity for making these things. And also you can integrate it with other things and do a lot of on-chip systems. Some of the challenges are basically addressed with these integration issues, integration discussion. And then the question is that can we take a power amplifier? So if you look at some of the standard power amplifiers for higher power generation system, they look like that, more or less. There's a module. There's some external passive components. There is a semiconductor die, sometimes a gallium arsenide, sometimes a other kind of compound semiconductor. And you want to see if you can convert it into a single chip device that sits in a single standard package and integrate it fully. So now for doing that, of course, what are the issues? So we have to think about what are the challenges that you deal with. The biggest challenge, perhaps, in CMOS for making high power systems is the low breakdown voltage, right? CMOS transistors, the way are very fast, and you make them very numerous. You can make a practically unlimited number of them on a chip, but it comes at a cost. The cost is that you make them smaller and smaller, which makes them punier and punier, which basically means that they have smaller and smaller breakdown voltages. That's the scaling. That's the concept of scaling. We talked about this when we were talking about device physics. Now, so that's one of the challenges we have to deal with. The other thing is that if you want to make it fully integrated, meaning that all of the elements are on the same chip for it to be repeatable and all those things, one of the other things is that you have on-chip inductors, for example, spiral inductors and all those things, but they're low quality factor. Basically mean they're relatively lossy because it's a very thin layer of metal and it's one layer or a couple of layers, and then you that you can actually use for this. I mean, there are more layers, but the thick layers are really the top layers. There are also other problems. If you want to have those inductors, for example, RF choke, AC blocks, things of that. So if you use the classical topologies like this, you have to run into all of these problems. So how do we deal with this? Now, before we talk about how do we deal with this, let's focus a little bit on the first issue of the breakdown voltage and do a little bit of a deeper dive into the device physics mechanisms involved. There are really multiple breakdown mechanisms, so let's talk about them one at a time. The first breakdown voltage, so we will talk about three general categories of the breakdown issues. One is what we call the gate oxide breakdown. So if you look at a typical transistor, which is shown on the upper left corner, and if you look at the voltage across the channel, and we talked about this again when we talked about the transistor, MOSFET transistor a while back, you see that actually the voltage across the channel, which is this red curve, grows slowly in the channel, and once you get to the pinch-off region, a good chunk of the voltage is dropped across there. So you have a small region where you have a large voltage across, which means that basically electrons start, or charge carriers, if it's a PFET, it would be holes. It will start basically accelerating from the edge of the channel towards the edge of the drain. Now, they start accelerating because they're subject to a large field, and then they accelerate there, and then they hit the drain, where the impact cross-section is pretty large. So they would basically be all of a sudden stopping there. So now, this is a challenge. This area is where a lot of things will happen, as we will see. Now, one of the breakdown mechanisms is basically, if you think about this gate oxide, by the way, the other way to make the transistors good and fast is to make this really, really thin. This is several atomic levels thick, maybe like 3 atoms or 3 layers of silicon atoms thick, right? In a state-of-the-art transistor. So you can imagine that actually what can happen is that if you apply too much of a voltage difference between this gate and the drain, then at that point you can have a breakdown, and then if there's a current flowing, for example, all of a sudden you can actually cause a catastrophic damage. An irreversible damage. So basically, at some point, your voltage exceeds something, you just basically charge passes through, current passes, damages the oxide, and the transistor is done. It's a probabilistic event, right? Like a lightning happening, right? Where does it happen? When does it happen? Depends. Certain conditions are more conducive to it than others. And it's determined by the quality of the gate oxide at this point, which is very interesting because it ties into the next one in the light of that acceleration inside that depletion region. So now the second mechanism, which is the hot carrier degradation, is that, again, as we said, the electrons start accelerating, and particularly in that region, and they will have impacts areas close to in vicinity of the gate and drain where they are coming close to each other. Now, we saw that that's where you usually experience a larger voltage difference, right? If you look at the previous plot, if you remember the voltages, basically here, this is the voltage, the voltage difference between the gate, which is the green voltage, and the red, which is the drain voltage. So this is highest here, and this is where you have all these hot carriers coming in and having impact. And they can be even so hot that they can actually release secondary carriers. Some of these electrons can get actually stuck in the in the oxide itself, bounce and get scattered and get trapped charges there. It can change the properties of the transistor slowly because of this trapped charge, or it can expedite the catastrophic gate breakdown itself. So it's generally a slow degradation initially because you have more and more gradual degradation of the drain region, but at some point it can also lead to a catastrophic gate failure. There's a third mechanism, which is interesting, which is what we call punch-through, which is basically when the depletion region associated with the drain and source, right, actually start meeting. The only reason under normal circumstances when the transistor is off, okay, there is no current between drain and source, is that you have two back-to-back diodes, right? You have an NPN, I mean in a MOSFET, right? The source and drain are N, and the channel area is P-type normally before it's inverted. And what happens is that if you apply a large enough voltage, these depletion regions will extend and start meeting or getting close, which basically means that there's a potential barrier lowering. And this will exhibit itself like these changes in the IV characteristics. So on the right-hand side, you will see that once you go beyond a certain limit, all of a sudden current starts pushing up. That's the current that's going through the bulk. That has nothing to do with the MOSFET, the surface channel on the MOSFET. It's just going through the bulk. Now, this mechanism in and of itself is not a destructive mechanism, right? It's just just a current flowing through the bulk. Now, but through heat, it can actually damage the transistor, and can also accelerate the hot carrier effect. So there are all these breakdown mechanisms, so we need to really think about what we are doing with the transistor to overcome these things. There are other methods to deal with these things as well, but let's focus on these three for now. Now, so let's go to the topologies of the power amplifier, different ways. So the idea here, the question is that how do we generate large enough power? How do we create large power using MOSFETs that have low breakdown voltages? So let's start with some basic topology. So this is the most basic topology, is the one shown on the upper left here in this plot. So you have some sort of an inductor or a choke that provides a DC current. Then you have the transistor operating as some sort of a switch, turning it on and off, and you have some network following it, right? Now, if you look at the waveforms associated with it, you can see where different kinds of breakdown voltages would be important, right? For example, you see that the drain voltage, the red curve, and the gate voltage, which is the green curve, are going to have the largest difference at the minimum of the input voltage and the maximum of the output, right? As it's swinging, of course, it's an inverting stage, so the drain voltage is going to be highest when the input gate voltage is the lowest, and this is where you are stressing the drain gate oxide the most. So that's where you are prone to that. Now, the hot carrier effects, on the other hand, are significant when you have both voltage and current, right? Because you have, and that's basically these like orange bands where the hot carrier is most pronounced. So the damage due to hot carrier will be happening there. And also, the punch through will be happening at the time where the excursion is the largest. So this is the kind of the stage that you're dealing with, and then you're limited by how much voltage you can tolerate. So at some point, basically, if I say, okay, I have a maximum gate breakdown voltage of 3 volts, it means that this voltage cannot exceed that. And it's not even a number like that. What happens is that it's usually specified in terms of the lifetime of the transistor, expectation of the lifetime of the transistor, in terms of the voltage you apply. So you can basically increase the voltage by 0.1 volt, and the lifetime of the transistor will degrade by a factor of 10, for example. But it's a statistical analysis, and that information is usually present in available from proper foundries. So this is one basic topology. So what can we do from a topological, from a circuit standpoint, to overcome some of these things? The idea would be essentially all of these ideas are based on one thing. Can you find a way to split these voltages among multiple stages? Instead of having one transistor carrying all the burden, if you have a larger number of them that you can basically, they can share the burden. Each one of them can carry a little bit of the burden, then you can do it. So basically going again from that mindset of going from the big elephant to the army of ants, right? It's another step. So one of the things you could do is this kind of alternative concept of bridge, right? A bridge amplifier. The bridge amplifier, the way it's shown here, consists of an NMOS and a PMOS. So if you can have an NMOS and a PMOS, and then both of them basically drive. So what happens is that this voltage, if it's, let's call it VBAT or VDD, the average output voltage will be halfway through. And the NFET and PFET are kind of like, more or less, if properly designed, will split their share of the voltage excursion, the voltage swing. And that way, each one of them experiences about half of that. So it reduces the voltage straight by a factor of 2x. The problem is that PMOSs are not generally as good as the NMOSs in MOS transistors, primarily because of the fact that holes are not as mobile as electrons. And then you have to also have the right drive voltage for these things, the DC voltages and all those things, which is doable. I mean, but it's some extra thing to worry about. And the voltage swing also is reduced because now your maximum voltage is VBAT, not VBAT, 2 VBAT, or even 3 VBAT in the case of a class E or something like that. Because in those cases where you have an inductor, like the previous example, that's the DC is centered around VDD, and therefore you can actually go above VBAT in that case, and you go quite a bit. You can go actually above that quite a bit. Now, what else can we do to overcome this thing? If, let's say, if you already have a voltage supply that's large, but you're trying to use transistors, MOSFET transistors that are capable of only handling certain minimum amount of, not a very large amount of voltage, right? So the other thing you could do, you could say, you know what? I make a DC to DC converter. I'll take the DC voltage, I make it converter, a buck converter, or whatever you want to, the different kind. This is a buck converter. That basically a switching converter, a DC to DC converter. I'll take whatever voltage I have, and I convert it to whatever voltage I need. And then I drive my amplifier with this. This is kind of like one of those trivial solutions, right? If it was patents, this would be a quintessential example of obviousness, right? Taking things that exist and put them together, which is fine. I mean, a lot of engineering is that. But that's okay. But it just, and the other problem with this is that this introduces other problems. First of all, this DC converter itself will have some loss. It's not going to be perfect. Then when you're doing switching, a lot of time you're introducing switching noise that you have to think about filtering and things of that sort, because that will get into your RF chain and start modulating your RF signal, creates spurious signals. It usually requires a large inductor that cannot be integrated on chip. That inductor will have to be off chip, which kind of now starts defeating the purpose of doing everything on chip and all those things. Now, nevertheless, there are scenarios where this is a useful thing to do. The good thing it does, it actually allows you to modulate the amplitude too, if you needed to do that. If you can, well, the question is how fast can you do this, but you can provide some amplitude modulation. You remember we had the scaling rule in the very beginning, that if you scale the VDD of a power amplifier by a factor of lambda up and down, we could scale the voltage and current and therefore scale the power. So by controlling this voltage, you can scale the power. In general, with the power amplifiers, switching power amplifiers, you can control their power by scaling their voltage. So now the other alternative, which is quite interesting, is using a cascode. Now, the idea of using a cascode is that, again, you have two transistors, but now this time you have two NFET, which are faster. And you can actually drive them in such a way that they are going to be splitting the total voltage swing. So in this example, you can see that, for example, this mid voltage between the two cascodes, the VD1, is shown with the orange level. And if you look at it, each one of these drain source voltages experiencing pretty much half of the voltage swing of the other one, right? And what this allows you is that by controlling this V cascode, you can actually adjust it in such a way that you split the voltage between the two of them and get a better performance in terms of the voltages. So now, of course, there are other things. You have now two transistors in series, so your on resistance is twice. So you have to make these transistors larger, which means that now you will have more capacitances associated with that. But this is actually a pretty decent example. The other thing that you can do is basically what we call the stacking of amplifiers. So you can make any kind of amplifier. So any of this, like the triangles on the left-hand side, the four that are shown here, are stacked. And each one of them is really essentially what? Each one of them is it can be a complex amplifier. It can be a Cascode amplifier itself. It can be any kind of topology. But you can now have them, the VCC, VDD of the supply voltage of one can be the ground of the other one. So in DC, they are stacked. So they share the same DC current, but the DC voltage is split among them. And if you properly design it, and it's easier said than done to do that, and I will talk about that briefly in a second, you can actually have the voltage divided in this example in equal quarters. So you get quarter of the VBAT on each one of them, and these voltages would be at 1/4 VBAT, 1/2 VBAT, 3/4 VBAT, and VBAT of these intermediate nodes. And this is an example of how that was done in one of the earlier papers that was published. But so here's the key. The key is that the challenge with these things is that the interaction between the power amplifiers. These power amplifiers start interacting because there are some fluctuations in one, there's some coupling of RF from one to the other one, and that interaction can create all sorts of very complex, very interesting, and sometimes very difficult to handle dynamics of control. So these intermediate voltages need to be well controlled if you want to do that. So now let's say, let's look at a practical example, right? Let's say we are trying to make a power amplifier, a CMOS power amplifier, to drive a 50 ohm load for a given amount of power. Now, generally speaking, if you look at a power amplifier, it has some sort of a supply connection, as it's shown here, and you have a harmonic and waveform control, which is basically the waveform engineering part of the thing. There is some impedance transformation symbolically shown as a transformer here. It doesn't happen always as a transformer. It can be an LC network or RLC network. A lot of times it is. And then you have the load. So let's look at a typical, a basic example. Let's say you have a supply voltage of 1.8 volt, for the sake of argument, right? And let's say your transistors, so basically, and then let's say you're trying to deliver power with this supply voltage. Let's say your transistor can handle twice as much voltage as a breakdown voltage. So let's say your transistor can handle 3.6 volt supply, which is pretty high for small MOSFETs. But let's just even use this. Even using this example, you will see how pronounced the issue is. So if I were to just take this amplifier and make like a standard analog amplifier, like the ones that the output stages that we drove, and even if you allow it to go above VDD by a factor of 2, by biasing it with an inductor in the middle and then letting it go above and below, the maximum voltage swing that you will have is from 0 to 3.6 volts, roughly, first order. And the amplitude is going to be 1.8 volts for that sinusoid that goes from 0 to 360, right? The amplitude is 1.8 volts. So what is the power delivered to a 50 ohm load? If you connect the 50 ohm load here, what do we get? You get VDD, you get the 1.8 volt divided by VDD V squared divided by 2R, right? And if you do the calculations for this voltage and the 50 ohm, you get 32 milliwatts. So if you were to directly drive the load, okay, we call this P direct, with that power supply, you get about 30 milliwatts delivered. That's the maximum power you can deliver. Now, let's say if you wanted to deliver a couple watts, right? Let's say you wanted to deliver 2.8 watts of power to a 50 ohm load. Now, if you wanted to do that with direct drive, what is the voltage swing? This is a basic calculation. You just solve for V in V squared over 2R equals the power, right? Which is basically this equation. So your voltage swing would be plus minus 16.7. So the voltage swing has to be more than 34 volts, which clearly this transistor cannot handle. A MOS transistor cannot. Now, if you use for example, a gallium nitride transistor, it can, but then you can't integrate it with the rest of your CMOS transistors and things of that. So it would cost a lot more. But yeah, so you can see the problem, right? So this ratio of the power that you want to deliver to the power that you can directly deliver without impedance transformation, given a voltage swing, is called power enhancement ratio. And we'll talk about it more explicitly. And it's an important parameter. So we call it power enhancement ratio because you want to enhance it from 30 milliwatts to whatever, 2.8 watts. So how do we do that? Well, we do impedance transformation. There are different ways to do impedance transformation. For example, symbolically shown on, well, it's not symbolic, it's schematically shown on the left as a resonant match. You can have single or multiple stage of resonant matches, like an LC matches. And each one of them does an impedance transformation, an LC match, or on the right-hand side with a magnetic transformer, you can actually achieve that. So let's look at the equations a little bit more carefully and see what they tell us. So imagine that you have this impedance, a single stage impedance transformation, LC transformer, and see how that performs. Again, it's a pretty straightforward circuit. It's an inductor and capacitor, and let's assume that your only source of loss is coming from your inductor, and it has some loss that can be modeled as some series resistance, right? And that's captured by some quality factor. So for the inductor, you can have a quality factor defined, a Q for that inductor. And then if you have a quality factor for an inductor, and the impedance transformation of this thing, which would be RL, R load divided by Rn, is Qm squared of the network divided plus 1. The passive efficiency, the ratio of the power delivered to the load to the power that goes in, is basically determined by 1 minus Qm over QL. And so basically, and then the power enhancement ratio, or PER, which is the ratio of P out to what we get from a 50 ohm load. So this is basically the denominator, P 50 ohm, is the power that your transistor would deliver directly to a 50 ohm load without this network. And now if you put this network in, you of course get more power because now you've done an impedance transformation. That ratio is basically, you can easily show, it's a product of the eta and R, the efficiency and the transformation ratio. Now, the interesting thing is shown here. If you look at the efficiency of the passive network, this RL network, right? Or RLC network, sorry. This single stage impedance transformation network, and plot it for versus power enhancement ratios that you would need for different values of quality factor of the inductor. This shows something remarkably, it's something striking. Actually, this is the equation that's being plotted. So you can actually solve for a pretty straightforward calculation. It's a pretty straightforward calculation. You can do it. It's on the right. Basically, it's shown what eta is. So this is what you see. So in the example that we talked about, like the ratio of 2.8 watts to 34 milliwatts, right? That's a power enhancement ratio of like 80, 90, right? So if you look at it at power enhancement ratio of 80, at inductor Q of 10, it says that your passive network alone, even if you had ideal transistor, would have an efficiency. You cannot have an efficiency higher than 10%. It means that you will lose a lot of power. Now, if you have a Q of 50, the situation would be different at that power enhancement ratio. I mean, it can be close to 80% max efficiency of the pure passive network. Nothing else included, just that LC. So this is important. This means that you cannot, I mean, if in the examples we encountered, if you want to make a watt level power amplifier in CMOS with transistors that have breakdown voltages of a couple of volts, you are in this power enhancement ratios of like 100 or so range. And if you're trying to make an on-chip matching network, you have quality factors that are in the range of 10 and 15. And therefore, it sounds like it's an impossible task. Or is it? OK, well, there are a couple of things. First of all, is that what we calculated was for a single stage LC transformer, transformation network. You can have multi-stage. You can say, you know what? The problem arises from the fact that you're trying to do too much in too few steps. In that example 1. If you want to achieve something more efficiently, you probably want to do it in more gradual steps. So instead of doing all of that impedance transformation in one step, have multiple steps. If each one of them does a little bit of impedance transformation, and you can improve it. And that is true. You can actually improve it. So if you take that, do that, and find the optimum number of stages that would give you the best power efficiency for a given power enhancement ratio, you get this curve. These curves are a little bit, you can see they don't drop as precipitously as the other one, but still they're not that good. So at a power enhancement ratio of 100 and a Q of 10, then it says the passive network efficiency is a little bit over 50%. So that's still a lot of power loss, just purely in your passive network, right? So the question is that, is there another way to think about this? Now, conceptually, when you're doing these things, you're doing what we call a resonance match. Right? So it's a resonant match. Resonant match means basically, this is an example shown on the left-hand side. You have an inductor and a capacitor and a load, and they are in resonance. Now, if you look at the currents and voltages, what you see here is that inductor current and voltage are both high. Right? So both the inductor current and the inductor voltage are high at the same time, which means that there's also a large amount of energy stored in the inductor. So if you look at the energy stored in an inductor, in this example of 7 and 1 conversion and all those things, is like 49 volt amps. Now, or this is the power per second. Now, if you think about this, now, if you compare it to a transformer, in a transformer, on one side you have large voltage and small current, small voltage and large current, and on the other side you have a large voltage and small current. So the magnetizing part of the inductor, which happens in the transformer, is storing a lot less energy. In fact, a factor of 7 in this example. Now, if you're storing less energy in your circuit, resonance circuit, for a given quality factor, considering the fact that the quality factor is the ratio of the energy stored to the energy dissipated per cycle, if your quality factor is fixed, then it means that the energy dissipated per cycle is also reduced by the same factor. So that's why using a transformer where there's a large transformation ratio, magnetic transformer, has a fundamental advantage compared to an LC. Now, if you do that, if you use a magnetic transformer, you can actually derive the efficiency in terms of this power enhancement ratio and other parameters. It's a little bit more elaborate calculation and all those things, and it's shown here. But in essence, you get some improvement. The improvement may not be as large. It's not exactly a proportional one like the simplified example that we showed, but it's a relatively decent one. Now, if you look at it now, it depends what, in the example that we talked about, if you're trying to make 33 dBm power out, which would be 2 watts, and use a half-bridge circuit, then what you're talking about is that your transformation ratio should be a factor of n. The transformer ratio is n of 8. Now, if you think about this, there are certain scenarios. If you want to just do a transformer like that, if you just were to make that transformer, the primary and secondary inductors would look very strange, because in this example, the primary inductor, the secondary inductor would be 4 nanohenry inductor, which is a relatively normal value for on-chip inductors. But the primary inductor would be 63 picohenries. And again, it's possible to make a 63 picohenry inductor on chip, but coupling them effectively to a 4 nanohenry inductor is very difficult. So the large disparity is significant. Now, if you were to do this instead of 33 dBm for 15 dBm, n becomes 1, and they both become the same value, which is kind of like a relatively straightforward transformer to make. So there's another problem still to solve, right? Which is basically, now, even if you wanted to do, even if you could do, if you wanted to do the transformer, making really good transformers on chip, at least the one-to-one, the transformers with one single input and single output in this format, is difficult. So there are other issues with this also, that there are the ground inductance and all those things. When you have the matching network, when you're on chips, you have wire bonds or solder bumps, and you have to think about the ground wire bonds and the supply wire bonds or supply bump, and those would also impact your overall performance quite a bit. So the question is that, can we come up with a way to solve this problem? So for example, if you wanted to reduce the bond inductance, right? So yes, you may come back and say, well, use multiple bonds, right? The problem here is that if you try to do that, then the mutual inductance between them starts lowering them. So if you two wire bonds in parallel next to each other, the inductance is not going to be half. It's going to be like 0.9 because of the mutual inductance between them. Now, you can use a lot, and you can get some reduction, but it's kind of like a brute force solution that's not really that effective anyway, right? The other thing is actually, for example, if you use a differential drive, at least as far as the odd harmonics are concerned, right, that node becomes a virtual ground. And for odd harmonics, and same thing with the VDD. So that way allows you to, that allows you to at least take care of some of the harmonics with whatever impedance you have on your ground and VDD. So, and that leads to some sort of, and you can basically in principle say, I can use some sort of a class E over F design, where you basically have a wire bond connection, or a solder joint or a solder ball, and then you can have a differential one, and you can overcome some of these problems. Now, the other problem for the differential one is that, yes, the differential is fine, but a lot of times your output needs to be provided as a single-ended output. for a variety of reasons. Sometimes your load, your antenna is designed, whatever you're driving is designed as a single-ended load. A lot of times you don't want to kind of like have multiple lines routed on your chip the same way. You want to go to ground plane on one end and have one line distributed as opposed to two. So you need some sort of a balun that converts the balance to the unbalanced, and hence it's called balun. And there are different ways. You can actually have some LC balance like the one shown on the right-hand side, or you can actually use some sort of a transformer-based one that's shown on the left-hand side, for example. And the good thing about it is that if you have some sort of an inductor like that, you could actually use a transformer, and the other side of it can be a balun. Now, but still we haven't solved the basic problem. The basic problem is that how can you make high-quality factor inductors that are coupled to each other magnetically, and they're small enough, but they're magnetically strongly coupled, right? Because we saw that for watt level amplifiers, we needed something like that. So one of the things that you can think about is that if you compare a loop inductor with a straight line inductor, if you could connect to it, right, which one has a higher inductance? So if, in other words, so let me specify the problem more clearly. Let's say you have a piece of wire, and then you take this piece of wire and turn it into a single loop. And the inductance of this single wire from one end to the other, compare that with the inductance of the loop. Which one has a higher inductance? And the answer, somewhat maybe counterintuitively for some people, is that the straight line has a higher inductance. And you may say, wait a second, where is that? How about this like spiral? We do loops and all those things. We learn all of those things that, we make solenoids and all those things to get more inductance. And the answer is that solenoids have multiple turns. That's why their inductance goes up, because it's a mutual between the adjacent turns that helps it. Another way to see this is that if you have, for example, two wires that are carrying current, and they are going in opposite directions, which is what's happening in the loop, the mutual inductance of these things actually is reducing the inductance. And one way to see that is that if you bring them very close to each other, in the end the magnetic fields cancel, and there's no magnetic energy stored in the space. Anyway, so if you could use these slab inductors, which is basically a straight line, they would be better, because then you can actually either for a given inductance, you can make them shorter and have less loss. Also, they don't have current crowding, things of that sort, and that would be nice. But the problem is you cannot connect to them properly. How do you connect to them? If you put a transistor here and a transistor there, then they are not going to be connected to each other, because you need an extra wire, and then that defeats the purpose. So the key is that, is there a way of taking these slab inductors and driving them in such a way that you get the same effect and take advantage of that? And also you need to be magnetically coupling to them. And the answer is putting them in a circle. So now, if you think about this, if you take these multiples, in this case 4, of these slab inductors, and for example, look on the one on the plot, the figure on the right-hand side, and look at the slab, let's say, on the right-hand side of that plot. You have two transistors on the top and bottom that driving it out of, it's kind of out of phase, asymmetrically. And in this case, you have a VDD that is connected in the middle, which is the virtual ground. So this is going basically, that slab is basically going up and down like this. Now, what you do is that if you put them in a loop, then the next slab is also going up and down, but out of phase with that. So if these are the two slabs, they're going like this with respect to each other in terms of voltage. And there are 4 of them, but I don't have 4 hands. So now the other interesting thing is that now that so they can actually connect the transistors, and the ground would be connected in between the adjacent transistors, because that would also be the same way a virtual ground as the connection between these two adjacent transistors would have been. The same way for the capacitor. Instead of connecting the capacitor between the two ends of the slab, you can take the same capacitor and connect it across two adjacent slabs, which are now physically close to each other, so you can actually make a good connection. And and from the perspective of the capacitor, the voltage it sees on this other end is the same exact thing that it would have seen on the other end of the slab. So from the capacitor's perspective, it can't distinguish these two voltages by substitution, right? And what happens is that this architecture allows you to have this is like an engine, right? Now it's kind of like you're driving it. It's a pretty strong engine. It's going around. Now what you need is some sort of a transmission to take this and get it out and connect it to the tires, right, for example. And that would be the secondary, which is shown here. So the secondary is taking this magnetically coupling to this engine that's going around, that's kind of circular. So there's an AC current circulating back and forth in this thing. And now you put a secondary loop here that takes that and magnetically couples that and then couples it to the load. And this is what we call a distributed active transformer. It's distributed because it's not in one place. It's active because every part of it is driven, and they're driven in multiple parts, and they can couple to the output. And another way to think about this is that you can think about each side of this thing, the part with the primary slab and the secondary slab, as a one-to-one transformer. And you have a one-to-one transformer there where on the primaries, you're driving the primaries of these things independently with this structure that we discussed. But the secondaries of them are put in series, which allows them to add the voltages. So now, on the primary, you can have a much lower voltage that your transistors can tolerate because they're driven independently. They're driven in parallel, really. Your primaries are in parallel, if you think about it. But your secondaries are in series, which allows you to add the voltage and generate that like 30, 40 volts voltage that you do generate here and drive the output with that. Now, that's not a problem because there are no active transistors on the secondary. It's just a piece of metal. And that can drive the 50 ohm load and drive the power that you need to. Now, you need to also think about what you do about your input matching. There are different ways to do this. This is one of the early ways of doing that, which basically you can see you can have another one. If you need an input inductor for matching, you can actually place it between the two adjacent transistors as opposed to across a full slab. And you can get structures looking like that. You will need some distribution network to get the power to these things. These are just demonstration of, these are not wire bonds. They look like wire bonds. They're just showing where the connection is to avoid making the plot even more complex. If you have a single-ended input, you want to convert it to a differential. You need another Balun at the input. And then that's basically something that looks like this. So this was the first demonstration of this distributed active transformer producing a couple watts of power at 2.4 gigahertz. And you can see the different elements. These are the primaries. The thick ones are the primary slabs. There's a thinner one, the secondary slab. Inside, there is a distribution network. These are the inductors for the input matching, and this is the input Balun. And then there are some variations that happen later. So this is another. This is the distributed active transformer of that. This is another example of that. It's not very clear on this picture, but anyway, so it's another kind of DAT structure that produces, like, again, 2.8 watts that came from the example that I gave. And if you want to see actually how the performance looks like, so these are the powers of the output power, gain, and PAE of that particular amplifier. And it's quite broadband. If you look at it, it's quite broad. Now, you don't have to do it in a square setting only. You can have as many of them as you want. Another example, fun example, is that you can actually make an octagonal one. You can make any kind of like polygon. An octagonal one will have 8 cores to drive it, and they are in series. So this is an example of an octagonal design that was done with different kind of distribution network. This is a picture of that die made with that octagonal design. And different people see different things in this. Some see a Ferris wheel. Some people see a turtle. This is the head. This is the body. Some people see a carpet. I don't know, whatever you see. Anyway. Now, and it can be done quite well. So performance-wise, this is very good and compares quite favorably to other things that were done in similar technologies at the same time. Now, the other thing is that now if you want to really turn it into an actual part that goes into your cell phone, for example, if you look for earlier dates where this was done many years ago for GSM GPRS example. So you have, for example, in this case, you needed 4-band power amplifier. So you needed a power amplifier that covers the 2 lower band, 850 megahertz and 900 megahertz, and then a higher band, which basically covers the 1800 and 1900 megahertz, 1.8, 1.9 gigahertz, and runs off of a lithium-ion battery, full power control. It can tolerate load mismatch and things of that sort. And so if you can do that, the problem here is that you have power supply limits. So if you make it the standard way, so this is the standard way, just like drawn like a rectangle, as opposed to a square. So you have 4 cores, and you have the primary and secondary. Now, of course, if you look at this, you will suffer from a breakdown issue, because if your voltage is 3.6 volt or higher, for example, when you put your phone on a charger, the voltage would be higher. Now, these transistors cannot withstand it. So the idea here is to use a double concentric design. So the double concentric design is shown here, and it takes there are a couple of interesting points to note about it. So here you have 2 sets of primaries, 2 primary loops as opposed to 1. And each one of them, of course, each core, if you notice, compared to the previous case, is formed of a cascode as opposed to a single differential pair. So that doubles the amount of voltage they can withstand. But now you have two primaries, right? But these two primaries are, so from a driving perspective, they are operating independently. But from a DC perspective, they are placed in a very interesting way. They are stacked, if you think about it. Because you look at the VDD. The VDD is for the outer primary, those 4 points. Now, the ground for the outer primaries are the common source point of this outer differential pairs, right? This normally would have gone to ground at this point. But now, instead of going to ground, it's serving as the VDD of the inner primary loop, right? You can see that the ground of this guy, these pairs, these cores, is basically connected to midpoint of these inductors, the slab inductors of the inside primary. So these primaries are now stacked, so which means that the voltage, the 3.6 volt or higher voltage, is divided between them. So each one of them experiences only half of that, sees 1.8 volt supply of that. And now each one of them splits that using a cascode between two transistors, so each transistor on average sees 0.9 volts of this voltage. So, but now they contribute power to they're both coupled to the secondary, right, in parallel. So both of them magnetically couple, and they are driven in phase, so they basically produce, each one of them produces half of the total power that's coupled to the secondary, which is in between, sandwiched between them, the darker, kind of like a red burgundy color, and then that's fed to the output. So this allows you to withstand the voltage. Now, of course, you need additional things. You need to have some sort of a power control, because in an actual power amplifier, you need to be able to do power control. Each one of them has some biasing control. That's a central bias. There's a sense and feedback. There's a sensor here that detects the power. There's a feedback loop that controls this and controls the power and adjusts them accordingly. So there's a lot more sophistication involved in that. And this became a commercial product that was sold in large volumes, but this is a picture of it. And basically, on the right-hand side of it, you can see the low band, the 800, 900 megahertz one, and then the one on the left is the high band, the 1.8, 1.9 gigahertz example. And these are some of the performance measures. Basically shows that the noise performance is good, the spectral, the spectral and temporal masks meet these requirements. It can withstand various kinds of load mismatch. So if your load is not exactly 50 ohm, it can still produce power. It doesn't blow up. It doesn't do all sorts of crazy things. It is very well controlled over different battery voltages or supply voltages from 2.9 volt to 5 volts. You can see the power control loop is very stable, and it does control it to within like 0.1 or 0.15 dB. And the power control, the power output versus the control voltage is pretty well behaved and monotonic. It's quite reliable. Many millions of hours of reliability tests it was done. The reliability test on amplifiers, on power amplifiers in particular, is very interesting. You get a large number of them, and then you have that elevated temperature and elevated voltage. And there are formulas that translate them to additional utility time. So if you use, for example, if you do 2 million hours of device hours of testing, which basically means that you have a large number of devices that are testing in parallel, and you can accelerate that, and you do it at higher temperature and higher voltage, you can accelerate testing, which allows you to test the long-term reliability of these devices. And these were quite reliable and predictable. So that's one other aspect. That's an example of a design that leads from a conceptual design to something that actually is a product. Okay, now there are other things. We talked about linearity, right, in the power amplifiers. And we can talk a little bit about that and going forward. Just briefly, some of the issues with linearity is that, like we said, I mean, the waveforms become more and more nonlinear, if you remember the discussion that we had. And the interesting thing is that the exact device characteristic is less important in a switching power amplifier. It's really kind of like the overall behavior. Now, there are a couple different, as a very introductory discussion of this, there are two different kinds of nonlinearity. And to show you the difference, I want to show you an illustrative example. So these two pictures show the two different kinds of nonlinearity. One on the left I will call a static nonlinearity. One on the right I will call dynamic nonlinearity. Now, the static nonlinearity is that if you have a nonlinear V in, V out, And this is a modulated waveform. That's why it looks like that. So you have a modulated, and the blue curve is the envelope of a modulated signal. So basically, this is a two-tone. This is a beating tone, right, coming in. And what you see is the envelope, but the actual carrier is moving pretty fast. And it's going through a device with static nonlinearity. Basically, it has a nonlinear V in V out characteristic. Now, you put it through that, through an amplifier, switching amplifier, and then there's no dynamics involved in it. And what you see is that there's a one-to-one correspondence between the input and output voltage. It's not linear, so you take that envelope and you turn it into something that looks differently, right? Now, there's something else. Now, if there's dynamics associated, if there's some delay and lag and memory in the system, you can put the same input in, but the output will look different. Now, you can see that there's no symmetry versus the middle of the waveform, which means that there's some buildup. For example, what can you do that? A slow time constant in the circuit, right? A biasing network can do that. A capacitance somewhere. A thermal behavior. If the device is heating up, so as it's going up, it's different from when it's going down. There are many, many things that can produce this kind of dynamic nonlinearity. And interestingly enough, of course, if you look at it in the spectrum, you ideally want to have your spectrum confined to a limited band that you have access to for a variety of reasons. You don't want to be creating noise for other people, and you don't want to be spilling over on other people. So you want to create some sort of a clean waveform that looks like that blue curve, right? Now, the green one is what comes out when you put it through this nonlinear system. That's the big problem with the nonlinearity in a power amplifier. What we call a spectral regrowth. So you can see that these parts that were clean when they go through that nonlinearity. It's basically, you can think about it as an intermodulation between components within the spectrum that you're transmitting. Different components are interacting with each other, and the intermods would appear outside the band. And these are in some other people's bands. So other people don't like it. So you need to get rid of them or minimize them. So the question is that, is there a way, first of all, before we even talk about how, is there a way to correct for those nonlinearities? In particular, well, the static ones, it's kind of straightforward. I mean, if you think about it, at least conceptually. If you know that you have a certain kind of nonlinear transfer function, V in, V out, you can apply the inverse function to the input, right? And instead of applying the waveform that you wanted to create, you apply it through the inverse function and apply that thing, and then it will produce the right output. The question is that, how do you fix the can the dynamic one be even corrected? And the interesting thing is that the answer is yes. And this goes back again to waveform engineering, right? So what you see here on the right, on the top right, what you see is the original, the dynamic nonlinearity. The blue one is the input, and the green is the envelope of the output, which is what is damaged, the spectrum, and the spectrum is shown on the left. So the spectrum of the blue is so there's a color correspondence between the spectral plot on the left and the temporal plots, the time domain plots on the right. So you can see that uncorrected, you put that modulated signal in, you get that green envelope, which is asymmetrical. Now, but the interesting thing is that there exists that other second blue one, which doesn't correspond to this spectrum, that you can put on the lower right, that you can put at the input, and it will produce the output that you require. So, but you can see that's also asymmetrical. So you design the input in such a way that it will produce the desired output. Now, how do you come up with this thing is a more interesting discussion. And again, we are not going to be able to have enough time to go into it, but there are some kind of like interesting ways of creating a network that has some certain kind of dynamics itself. And one of those things is basically creating the preamp predistortion waveform based on a system with memory. So, for example, you can also make a tap delay line structure with nonlinearity that has various elements of the input signal delayed and then added with different weights and different nonlinearities, which allows you to produce that kind of input, call it a generalized nonlinear memoried predistortion, that you put into the amplifier, and that can produce the output that you want. And that would give you the kind of correction method. So that's a very, very introductory discussion of power amplifiers. There's a lot more And there are a lot of interesting architectures which we didn't talk about, like power mixers, power DACs, things of that sort. Power mixers is basically where you're doing your up conversion mixer, where you're doing your power combining, and you do it in a binary weighted fashion. You can actually add them. Or you can have a power DAC, where basically you can have different power amplifiers with different powers combining together, and you're just doing a digital up conversion. You basically, depending on which ones you turn on and which ones you turn off, you basically have a power digital to analog converter whose output is a power at the frequency of interest controlled by that. There are lots of different variations on this thing that we are not talking about today. But hopefully that would give you a little bit of an introduction as a starting point to think about power amplifiers. Okay? Any questions?